In the space surrounding an electrically charged body, there exists an electric potential which is proportional to the charge Q and inversely proportional to the distance r from the center.
You see, in the space surrounding an electrically charged body, there occurs an electric potential which is proportional to the charge Q and inversely proportional to the distance r from the center.
Here we're looking at the electric potential and the electric field of a charged metal tube. This is, we slice a plane lengthwise through the center of the tube, and we're looking at the potential and the field inside the tube. As you can see, the electric potential is very high inside the tube, but the electric field is basically zero inside the tube. It's only high outside the tube. There's a little bit of electric field bleeding in from the outside at the ends of the tube, but we're not going to worry about that. Now, electric potential is analogous to air pressure. That's the way Maxwell thought of it. It was simply the air pressure of the ether. The electric field is simply the difference in the electric potential as you look from one point to another. So here's the electric potential of our charged metal tube. And let's see what happens if we vary the amount of charge on the tube. Now, outside the tube, the electric field is high, significant. If we vary the amount of charge on the tube, then the time derivative of the electric field is also going to be large. And as we all know, a time-varying electric field induces a magnetic field. So outside of the tube, if we vary the amount of charge on the tube, you're going to have an ordinary, run-of-the-mill, transverse electromagnetic wave that's made out of electric fields and magnetic fields. But now let's see what's going on inside the tube. Inside, the electric field is zero. So even though if we vary the charge on the tube, the time derivative of the electric field is also going to be zero. So there will be no induced magnetic field. So you might look inside there and say, oh, there's nothing going on inside the tube. But there is something going on. The electric potential is very high inside the tube. And as you vary the amount of charge on the tube, you get a time-varying electric potential, which is a very important thing. We've put it back into Maxwell's equations. The life energy, or the Prana, as it was called in the Vedas. Or if you read the Christian New Testament in the original Greek, they use the words psyche and Pneuma to indicate the life energy. It's what your soul is made out of. It's induced by a time-varying electric potential. Just like a magnetic field is induced by a time-varying electric field, the life energy, or Pneuma, or Prana, that's induced by a time-varying electric potential. If you're going to say, oh, well, gauge invariance, the potential's not really physical because of gauge invariance, you should read this paper, published in the Physical Review, August 1st, 1959, by David Bohm, Significance of the Electromagnetic Potentials in the Quantum Theory. David Bohm was a student of Oppenheimer's, and he had difficulty graduating from university because his senior thesis was classified, because he worked out some mathematics that pertain to the Manhattan Project. So let's see what Dr. Bohm has to say about the electric potential. It would therefore seem natural at this point to propose that, in quantum mechanics, the fundamental physical entities are the potentials, while the fields are derived from them by differentiation. So he's saying the electric potential and the magnetic vector potential are the primary fundamental entities that we want to work with, and the electric field and the magnetic field are secondary things. The potentials must, in certain cases, be considered as physically effective, even when there are no fields acting on the charged particles. Here he's talking about inside of a charged metal tube, where the electric potential is very high, but the electric field is zero. If you shoot an electron through that tube, the electric potential is going to affect the electron all by itself. We may try to give a further new interpretation to the potentials. In other words, we are led to regard the electromagnetic potentials as physical variables, This means that we must be able to define the physical difference between two quantum states which differ only by a gauge transformation. And this is a polite way of saying that gauge invariance is malarkey, because the potentials are real things. You can't just arbitrarily change them around. So these are the equations we plotted to get those pretty pictures. Here's the variables. Thank you very much. Good night.